Welcome everyone. Thank you so much for joining us today. Thanks for your time. I'm quite actually excited, because it was like a long time dream. Because whenever I check the list of the winners before the previous ones, I really feel proud. Kuming Cheng, one of them, actually is here right now as one of the icons in my field. So I'm really feeling proud and feeling happy. Thanks for coming, everyone. Today I want to talk about a kind of new. Not that new, but a kind of new insight about mineral exploration, but under uncertainty, because we are talking about a kind of decision making. And in petroleum engineering, for example, or geotechnic, we consider risks, but still we are way behind in geosciences, especially in mineral exploration. So we need to make a better decision considering the risk and uncertainty in every part and scenarios of our analysis. But before I go to the scientific details, I would like to appreciate all the nominators who nominated me for this award. The main nominators are Fritz Achterberg and Eric Gronsky. And the rest of them, David Cohen, my PhD supervisor, Dietmar Muller from Sydney University, my postdoc supervisor, Jennifer McKinley, as always, thank you so much, and Rem Guangzhou, an old friend. Actually, we've been friends for over 10 years, but the first time I met him in person finally was a few nights ago, thanks to IAMG. Then Vera Pawlowski-Glan, thank you so much, always supportive. I learned a lot, and I'm still learning from you. Thank you, thank you. And congratulations to Shauna Morrison, my other nominator, who received this award as the female awardee. Back in the day, 12 years ago, when the first time I met Fritz Achterberg. At that time, I was doing my master thesis, and I met him in a conference, international world mining conference, actually in Tehran. And I was quite excited. I couldn't even breathe when I met him, because the only thing I could do was actually reading his papers. And because he has published many great, fantastic papers with his PhD students, who are actually great scientists and icons in the field, Kuming Cheng, Eric Gronsky, for example. And just because yesterday Steiner and Jennifer made a good point about trusting youngsters, just want to raise this issue, actually. I wasn't confident enough to approach Fritz because he was a big name. He had a big name. And I was just a tiny master student. And what happened here was a funny story. My mom called me and said, "Okay, have you met Fritz?" Then I said, "Yes." "Okay, what happened?" And I said, "Nothing, I met him." "Okay, no talk, nothing? No details?" And I said, "No, I just met him, but yeah, I'm quite proud." Then she said, actually, "You didn't meet him, you just saw him." It's a big difference between meeting someone and seeing someone. You just saw him, you didn't have a talk with him. That's a shame. Tomorrow you go, talk to him, introduce yourself, have a good conversation. I know he's an icon, but be sure he's quite approachable, humble. Otherwise, I come to you next week, and I will hit you as much as I can until you die. It was the first and last time my mom was quite serious like that, because she's my best friend, definitely, and she's actually my best dude. Fast forward to 10 years later, in Encyclopedia of Mathematical Geosciences, we published a book chapter with Fritz, and I'm quite proud of that. I wish he was here, but I'm in touch with him, but unfortunately he's not here, but just wanted to say thank you. And please, trust youngsters. They need your trust. So just at a glance, I would talk about different topics, but mostly related to the errors and uncertainties we have in each parameter or steps of our analysis. I mostly focus on geochemical analysis, but in the end, you can apply this to any types of data set you have. I mean, geophysical, remote sensing, whatever, or you can combine them all together and come up with a better decision, just because this is just beginning. And I will talk about some classification methods, their pros and cons, and why I use some of them, and why I developed some new classification methods. And then I would talk about their uncertainties in terms of the classes, thresholds, also the final maps and models, and I would talk about a kind of decision-making algorithm as well. But what is really important here, you can apply all these methods in 2D and 3D, it doesn't matter. The examples I have here are actually in 2D. And some happy news in the end, so hopefully you like it. So what you see here, this is actually my favorite cartoon, and I always use this as a kind of good representative thing for exploration, mineral exploration. We are like these blind people here, especially in greenfield studies. We have no idea what's going on there, especially in greenfields. So we need to take some new samples. It could be different samples, could be similar samples, could be geochemical, could be geophysical. So it means different data layers, right? But because we are still blind, we need to make sure. We need to come up with some probability as well. So we try all this several times. For example, I touched the tail. I'm blind. I have no idea about that. So it's something lined, smooth, some hair on. It moves. So it could be snake. Next time I touch it better. So I feel, okay, it's tail. So I do this several times. I come up with the legs, ears, everything. And at the end, I would come up with the whole shape of that elephant. Why we do this? Because we need to visualize everything. As a humankind, I need to visualize, I need to imagine that. That's why we do modeling. I mean, geomodeling. And through that, for example, you do some dimensional reduction analysis. Why? Because you need to come up with better understanding what's going on in our data set to find a kind of relationship between the values. Otherwise, they are quite complex. You can't understand the relations. So, as I mentioned in geosciences, mineral explorations towards, mining, excavation, we are still quite behind in terms of all sorts of uncertainty and their understanding and studying and making decisions based on that. But as you see, and Graves and Santosh made a good study. It was a good step ahead, actually. But for different phases of geology, geological studies, exploration, then to mining. And they consider the risk, but these risks are still mostly related to financial risks. And but what I would like to talk about is going one step further to front and talk about the uncertainties in our models, our analysis, everything we can imagine. So my main focus would be on target selection in the end, as the favorite parts actually to go there, take more samples, or do more studies, geological studies, and take more, discussions even about that to come up with a better understanding about those specific areas, target areas. But one of the main problems in geochemical studies, exploration geochemistry, is always lack of data. It doesn't mean it's dense, it's sparse or something. We always have some samples. Could be regular sampling network, could be irregular one, could be dense, could be sparse. But anyway, we have some samples, and we have no idea about the values in between. For example, in between two samples, we have no idea. So we use some interpolation methods just to come up with a better trend and better imagination. And to come up with some values for those unsampled areas based on the sampled areas. But why this problem happens could be due to some poor management, and it has some other reasons. I'm talking about some reasons in industry. Lack of money, lack of time, lack of access. We all experienced a pandemic. And these days, politicians, political issues. So we have very limited access in to some areas. Also, lack of experts in our team in some specific field, and some errors in computational analysis and even lab analysis. So these are all together could come up with a larger error in the end. So as I mentioned, we use interpolation methods just to come up with better understanding about the trend of the mineralization and have some values. But interpolation means estimation, and estimation is error. So as you may know, we have two main type of uncertainties in geochemical analysis, stochastic and systemic. One is related to quality and variability of geochemical data. The other one is mostly related to data analysis and interpolation. And we can't do too much about the first one, but for the second one, we can do that to reduce that. But it's always good to have some idea about these uncertainties and a kind of probability model. Next to our final model, we can make a better decision. And I'll show you how. But another point I want to raise here is actually this issue, misunderstanding of geology and geochemical processes. Yesterday, again, Jennifer McKinley made a good point, and she said we need to trust geologists as well. We can't go just strictly to some data analysis or any type of theoretical analysis and ignore geology, because sometimes they have some conflicts, and we need to come up with a kind of to compromise together. Otherwise, we can't trust the final models. So as I mentioned, we have different sources and sorts of errors. So all these together, if we don't consider them, all these together come up with some kind of error propagation, and the final error would be a huge one. So we need to consider them. If we can reduce them to reduce the final error. But what if, based on our models, just models, we say we have something in some specific area, we go there and we don't see anything? Or vice versa. For example, we say there is nothing in somewhere, and we go there and we see some mineralization anomaly. This is one of the biggest problems, again, due to those errors. These two guys are thinking the same thing, but from different points of view. So we can say both of them are right. This is what I always make as a kind of example as well. If you ask me what's the background color, I have no idea if it's black or white. This is some kind of conflict between the points of views. So in 1989, Rosenthal actually created this table, kind of matrix, based on the anomalies and backgrounds in our models, and also the real anomalies and backgrounds. And they come up with two different types of errors. If we say, based on our model, we have some anomalies, and we go to that specific area and find, okay, there is some anomalies, correct decision. If we say there's a background and we go there and we find that background and actually no mineralization, no specific mineralization, okay, we say it's a correct decision. But if we say we see some background in our model, but we go into that area and we see some anomaly or mineralization or deposit, is type 1 error. Type 2 error, if we say there's some anomalies in our models, but we go there and we see there's nothing over there, is type 2 error. So Carranza, in his book in 2009, came up with this matrix and formulated that actually, overall accuracy, based on true anomaly, false background, and true background. But as you see, again, a few years later, some other geologists, they said, we have no clear determination for B and D, false anomaly and true background. So, as you see, again, we have some conflicts. We have some different points of views. Which one is correct? Which one is more correct? So, as you see in here, for example, I talked about different classes, background and anomalous classes. So we use different methods, for example, to come up with those classes from background to strongly anomalous, weakly anomalous. Traditional statistical methods, they have their own pros and cons. Because these kind of methods normalize the data set, you remove the outliers, you manipulate the whole data set, and you don't consider geology that much. You just go through that with some data analytical stuff or numerical stuff. Same with EDA. You just use statistical and graphical methods, but you don't consider geology itself actively. What I mean by actively, it means we need to integrate these models actively with geology, because mostly what we do is actually interpreting those results geologically after making those maps or 3D models. But have a look at all these things in nature. What do you see in these? Something similar in all of these. As you see, these are actually repeating their structure in different scales. We call that self-similarity. And we have some kind of self-affinity as well, which is actually a kind of statistical self-similarity. And self-repetition as well. This is what Bernard Mandelbrot, in his fantastic book in 1983, developed as a new geometry, fractal geometry. Fractal geometry is different from Euclidean geometry. In Euclidean geometry, you have 3 dimensions, 1, 2, 3. But in fractal geometry, it could be decimal as well. And in these analyses, you don't remove the outliers, you don't manipulate your data set, and you use the whole data set you have. Still, it's been using in different research works, not just in geosciences. As you see, this one is quite new. I was in the train coming to Trondheim. I just saw that. Don't ask me about this because I haven't read it, but I know some part of that is about fractal geometry. But it's about its relation with genetics. The other one is for cancerous issues in skins. So, as you see, in medical stuff, they use medical studies. And in geosciences, Qiuming Cheng is here. He developed concentration area based on the relation between the area of the contour lines in any specific areas and their relationship with the concentration of the values. Then, same for concentration perimeter. Then spectrum area, singularity analysis, and their 3D formats such as concentration volume and 3D format of number size, and many other methods. Heaps of methods are out there. I'm not going to go into details of these methods mathematically, but what I want to raise here is actually most of these methods are, again, passively considering the geology, because they are mostly working based on some mathematical relations between the values and perimeter, area, distance, something like this, but not geology itself directly. And they work mostly like this, as you see in this log plot. For example, for number size, logarithm of the number, cumulative number of the samples, and the logarithm of their concentration values. Why we use this log plot? Because the fractal has the main formula or equation. If you calculate its logarithm, you come up with straight lines. That's why we fit some straight lines like this to these plots using least square method, for example, and we come up with those cross points as our desired thresholds. And for example, this one could be our background, weakly anomalous, moderately anomalous, strongly anomalous, very strongly anomalous. Then we make a kind of 3D or 2D map based on those different classes. But there's still one problem here. For example, in this one, number size, we didn't have any. We had a kind of gap here. We weren't sure if it's a class, a new class. What we did in 2015, we developed actually simulated type of multifractal models, as you see here, based on heaps of realizations, and we came up with this class and with some probability. So it made us sure to some kind of classification, I mean, new class. But anyway, as you see, different thresholds, I mean, the uncertainty in thresholds. So I said, yeah, we need to integrate the geology actively in our models. That's why I developed some new methods considering that geology. Concentration, which is Fritz Achterberg's favorite method. Concentration, distance from centroids, category-based models based on the rock types, and simulated multifractal models. 2 case studies, one is Sweden, one is Cyprus. The one in Sweden was actually mainly based on till samples, and as you see, throughout the country, and the target mineralization was VMS copper. As you see in this map, it's not that dense, but it's regular. Why we chose this? Because the geochemical atlas of Sweden is available, it's out there, and so we could trust that, we could interpret geologically, we could compare our results with whatever is out there. And yeah, I have applied some multivariate analysis to our data, I mean, to come up with the other relevant elements with copper. And, but if you want to know further about how to use, for example, compositional data analysis, what method in specific CLR or ILR, OLR, we are actually publishing this paper hopefully soon in a special issue at JGE. So you can later come up with this paper and now how to choose them. Because again, if you choose a wrong method, again, you come up with wrong results. This is another source of uncertainty. The other case study, Cyprus, the difference between this and the previous one, the density of the samples are quite high. I mean, it's quite high, and it's not regular. Because in regular sampling, we may or may not miss the orientation or trend of the mineralization. So I tried both to come up with some results. Again, the geochemical atlas of Cyprus is also available out there. Concentration multifractal model is actually based on the relation between the concentration of our target element and its highly correlated element. So you come up with some correlation coefficient methods, Pearson, Spearman. But for further details, you can read this paper. For example, you can use this correlation. This is what I highly recommend. This is a kind of new correlation developed by Professor Chatterjee at Stanford University in 2020 and 2021. It's not that sensitive to outliers, noise, anything. It's quite quick and fast compared to Pearson and Spearman because it has a really simple formula. And there is a Python package out there if you want to have a look. But yeah, for example, you can classify gold based on moly or copper and interpret that geologically even better. The other thing, the other issue, when we deal with catchment basin data sets, for example, stream sediments in catchments, we have some kind of issues such as this, dilution effect. From the source, as you see, the concentration goes down gently based on the distance. This is one effect. In glaciers, when you take some till samples, you have the issue of transportation. We have some formula for that, for example, just to consider it. But again, I considered that in Sweden because I was working on glaciers, because we take some samples from here, but it could be from somewhere else. So we need to consider that transportation, otherwise we get some shifted anomalies. How it works, actually, it's based on the distance between any specific known mineral deposit in that area and the samples in the whole area. For example, it works like this. These are the samples we have. These are the known mineral deposits, the VMS ones. But how we come up with the distance between them, we use centroid points. these are all polygons, so we need to represent them as some centered points. These centered points could be inside the polygon, could be outside, depends on the shape and geometry of that polygon or mineral deposit. So per case, we have some distances from the samples, and if we classify those concentration of the samples based on those distances, cumulative values of them, we come up with different scenarios. And the average map of those different scenarios would be our final map. For example, this is based on the initial data set. This one is based on the compositional one. You see the difference. This one has a better overlap with the known mineral deposit. It's actually behind that. That's why you can't see that, but you see the difference anyway. Same for Cyprus again, CC model and CDC. But back in the presentation Jennifer McKinley yesterday delivered, it was a nice one actually. It was about geogenic and anthropogenic analysis. I applied this method to some very tiny area. I mean, in Limassol or Limassol in southern Cyprus, as you see, this tiny area, and it's highly covered by agricultural zones and urbanism. So we had some anomalies for some specific elements, but we weren't sure if they are natural or due to contamination or urbanism. So I applied this method with David Cohen. We came up with some results, again, for some specific elements, such as nickel, chrome, lead, and silver. So generally, if you get some classic log plus, something like this specifically, it means, okay, it's something natural. But sometimes you don't get any classic plot. So it means, okay, something is wrong there. So probably it could be, it would be better to go there and check it out to make sure if it's due to urbanism or not. And we checked it out. And for example, for indium itself, yeah, it came up with some bad results, and it would say, yeah, it's due to urbanism. So this could be a kind of key, which works pretty well, actually. And for those cases, you can have a look at these papers. This one is mostly related to that contamination stuff. But the other method to consider the rock type, we have, for example, in the whole country, we have some main rock units, rock types, and we collect some samples throughout the country. So, but we need to consider their area, the rock type those samples are coming from. So, if we imagine each of these colors are different rock types, so we have some specific samples per rock type. They could be sparse, they could be dense. So per scenario, we have different ways. For this one, you can come up with the mean value of the samples per rock type, then apply some Monte Carlo simulation, and come up with higher number of values, then classify them. Otherwise, if they're not sparse, you have enough samples, for example, you can directly apply Monte Carlo simulation per group of samples, per bedrock, and come up with the whole values, whole samples, a large number of samples. For example, in Sweden, we had around 4,000 samples, 3,000 samples. We can simulate 10,000 and then come up with a larger number of samples, then classify those values. And this is how it works, because I didn't have any other case study like that to consider both types of samples, sparse and dense, just applied it to same data set. And you can see that in this paper, all the details and the methodology. But as I mentioned, we developed simulated multifractal models as well, just because we weren't sure about the probability of that, those classes we classify using any of these methods. So we applied that method actually to the realizations. For example, if we generate 1,000 simulated map or realizations based on the similar data set, Then we generate the E-type map, the average map of all those maps, and then we classify those maps using any of these fractal models. And you can find two main papers about that in these two. But as you see, we've got different results using different classification methods. So, for example, in industry, we have no time to go through all the methods. We apply that, we use some methods, and we come up with some 2D or 3D models, and we say, okay, let's go there, do some mining excavation. So, but the question is, if we use heaps of these models, which one is more reliable? As Bach says, all of them are wrong, but some are useful. And he means by that, actually, he means we need to consider that uncertainty. So for numerical analysis, for example, it's like dicing a toss several times. If you generate one map, it means that map is 100% correct. So we need to generate that map several times, simulate that to come up with probability. If we try that 100 times or 10 times, then we can say, okay, we see these similarities 10 times or 8 times, 80%. So we come up with some probability for our decisions. So here, for example, for those thresholds, using any of the methods, I applied Monte Carlo simulation to come up with P50, P90, and P10, and I calculated uncertainty, as you see here, based on P90 and P10, and we called this return, and this one could be our risk. And then we can come up with some plots like this, per element, per bedrock analysis, and per model, and per class. For example, per element, in this case for Sweden, you see all the returns are higher than the uncertainty, so we can say, okay, we can go to the next step. Otherwise, we need to consider our samples, our values, our analysis, lab analysis, to see if something's wrong there, or we need more samples or better sampling. Same in here for bedrocks, for example, in Sweden, you see the first three ones are actually more acceptable, although this one is so-so, this one in the middle. But these three are still critical because, as you see, the P50 or return is lower than uncertainty. Same for classes. For example, for one of the classes in Sweden, as you see for strongly anomalous, using any of the methods, classification ones, some of them are introduced here right now, you get some return values, you get some uncertainty values, and you can compare them together, and you see, actually here, number size is one of the best, singularity is one of the best, still, although the uncertainties are quite similar, not in these three cases, but still these two are quite acceptable. So if you generate some maps using any of these two models, we can consider that, okay, the strongly anomalous areas are more reliable for further sampling, for further studies. For Cyprus, same issue here. For all elements, it worked pretty well, except indium. It's not a big deal, not a big difference, but you can put it away, or you can consider that uncertainty. And same for it, for different classes using different methods. For example, for very strongly anomalous, some methods didn't give us any classes. But again, as you see, the return is quite high in number size, and risk is quite low. So we choose this one, or even SA is quite acceptable. The other uncertainty is actually related to the maps. In general, maps themselves are quite complex, especially if you simulate them. As I mentioned, again, one map means it's 100% correct. And this is not that reliable. That's why we generate, for example, 1,000 maps based on the initial data set we have. But as I mentioned, they are quite complex, and we need to come up with better representation with these maps. So, because we need to come with their uncertainties, spatial uncertainties, how we represent that by their similarity or dissimilarity as a kind of representative for uncertainty. How we do that using distance-based methods? You can apply, for example, Euclidean. If you work on some fluids or time series, something like this, you can use other type of methods, Hausdorff distance, Mahalanobis, but yeah, different cases, different scenarios, different distances. In here, we used Euclidean distance. Also for simulation, we used a sequential Gaussian simulation. And Michael Persch made my life easy actually today. He talked about that simulation. Also, he talked about MDS, multi-dimensional scaling. Because you can easily use that method to come up, to reduce the dimension of the values and come up with a kind of 2D or 3D plot like this. And these samples, we call that connectivity distance. These are representing those maps. These ones in this area, which are closer to each other, this means these are more similar. More similarity, more certainty, spatial certainty. So anyway, we go further based on all those representative samples. We put them in this plot. As you see, the uncertainty goes up from up to down. It's versus to return. And return goes up from left to right. And we categorize that like this. 9 different categories. The best category is this one, because it has the highest possible return and lowest possible uncertainty. So instead of making the average map or E-type map based on all these 1,000 simulated maps, we only focus on the average maps of these. And we come up with these 2 maps. One is based on the frequency framework, one is based on Bayesian framework. And based on the overlap between these 2, we come up with that category 9 areas. So these are the best possible areas. It doesn't mean if you go to any of these pixels or areas, you definitely find some very rich target element or mineralization or something. But it means it's the highest possible one with the lowest uncertainty. So it's quite probable. Also same for Cyprus. The red stars are actually those target areas. We double-checked them all. It's in progress for further interpretation. You see some of them here. But some recommendations, actually, as I mentioned, you can apply these to 3D models as well. To your drill course, you can apply this to remote areas, for example, Central Australia, for example, or even other planets when you have very limited number of samples. And you can apply this together with some other data layers, geophysical, remote sensing, geochemical, geological, and using machine learning methods. Also, as I mentioned, it's a pretty good decision-making process for the mine planning, exploration planning, supply chain, and risk assessment. So this was the scientific part of my presentation, but also some good news for the youngsters again. We have some postdoc position at CSIRO in Australia, in Perth, Western Australia, with Jun Hill and Fan Huang. So if you want to apply for it, the deadline is actually the end of the month. You can easily scan this QR code and go through the application. Also, I'm heading to the US next month, so those American fellows here would be great to have a catch-up and communication together over there. I'll be there for 10 months, and I'll be hosted by Shauna Morrison at Carnegie in Washington, D.C. as part of my Fulbright fellowship. Also, Jennifer McKinley, Qiuming Cheng, and Fritz Achterberg, and Daya Saga, they did a fantastic job by publishing this fantastic encyclopedia recently. And I'm really proud to be part of this book with 8 chapters, but just wanted to let you know next year, this time hopefully, my own book would be out there, which is related to multifractal modeling in geosciences. So yeah, feel free to reach out if you have any question, if you have any recommendation. And just want to say thank you to all the nominators again. Also, courtesy of Jeff Kers, because the last slides about those geospatial analysis was managed with Jeff during last months of my PhD, and it's still in progress, and hopefully in the US we finish it up. Also, IAMG organizers, especially Stena LFMO, and his fantastic team, thank you so much. We have a lovely city and a lovely country. Thank you so much for hosting us here. And yeah, thank you. Just let me briefly say something. This is one of the iconic creatures in Australia, black swan. You see that in Melbourne, but mostly in Western Australia. Indigenous people call that Mali. So if you come to Australia, if you see some indigenous people, say hi to them. And if you see some of these creatures, yeah, they tell them, yeah, we know something. Yeah, it's Mali. And they really like it.
You finished rather early, so we've got 2 minutes or so for questions. Sorry. Is that on now? Yeah. We've finished rather early, so at least 10 minutes for some questions, if anyone wishes to.
Gerald. Let me give it to him.
Okay, have you got another one to go up there, or that you need to?
No, this one.
I'm not sure if I was first, but I've got a question on the way you use return or define the way you return and risk or uncertainty. I'm asking because I would do it differently, but maybe that's also disciplinary background. So why do you define them the way you define them? Like P50 and P10?
Yeah, in geostats, we mostly focus on those, P10, P50. P50 is mean, by the way, so put it away. So P10 and P90, but in different cases, you can apply different ways. But mostly we consider P10 and P90. But again, it gets back to that conflict of point of view as I mentioned.
Yeah, I'd like to discuss with you why you would use average and variance there. Yeah. But let's keep it for later.
Yeah, sure.
Oh, we had someone.
And Gerald and Kimi.
Yeah.
First, congratulations for your prize.
Thanks, Roy.
I enjoyed the talk. Excellent presentation. There are one question is my comments. And the question is about you're attached to the statistics or fractals to geology, which is very good. Now, what are the physics mechanisms involved to create these similarities of concentrations versus whatever scale? Let's see, concentration area, concentration of volume, and number and the sizes. Those are equivalent or linked in terms of concentration against the scale. That scale could be area, could be volume, could be number, could be length. But there should be the similar kind of principles. So what are the physics can guarantee you expect the anomalies follow this kind of self-similarities or fractals?
Right.
That's one question. The comments is about, I can see that you named a number of methods, CA and CC and C distance, but to me is that they are equivalent, and that is the concentration against the scale.
Yep.
Scale could be distance, and as I said, the C and the C, the concentration, it could be let's say the 208. We did the posterior probability. This is you can consider as a concentration against the areas formed by integration of geological patterns. That's kind of your category, classification.
Yeah, that's correct.
So there are a lot of say, the links or the equivalents, I would say, although the forms are different. So whether
that's true.
it's better to give different names or whether to give just to use them differently with the same method. So that's just a comment for you to consider. So the question is about the physics. What geological processes, why we expect the self-similarities and among the,
that one I actually just wanted to clarify the geometry itself. But by that, I didn't want to, introduce any methods. Just wanted to say, that geometry works like that. But then, based on what I mentioned, the main formula, if you come up with the logarithm of those formula, both sides, it would be the straight line. That's why we fit those straight lines to the final log plot to come up with the cross points. Was it the question? Was it the answer you were after?
Okay. I'm expecting more of a physics. For example, we're talking about a fractal density. The density defined based on fractal geometries.
Right. Yeah.
Okay. Therefore, that's give you the concentration against whatever scales, and that is kind of a new physics.
Yeah. This is what the point you also mentioned during your presentation a few hours ago. Yeah.
Thank you.
Thank you. Congratulations.
Thank you.
I was wondering about one of your graphics in which you suggested that there is an area which you recommend. I think there was an efficiency boundary there. And then the lines, the separating lines of those recommended area to the rest was vertical
you mean the
and
categories,
horizontal.
right?
So
The categories, you mean?
Yeah, the categories. I think so. Yes.
These ones?
Let's take this one. I thought of another one, but you say, essentially you recommend the category 1, but why would the recommendation be separated by these horizontal and vertical lines and not by something with a different shape?
Yeah, that's a good question. Because this is actually, as I mentioned, this is still in progress. So with Jeff, we are working with this, but this is just the initial idea. But we definitely use different categorization methods to come up with better classes. It's not just. It's not going to be always like this.
Oh, okay, it's just the step.
Yeah, yeah.
Okay, thank you.
No worries. Because definitely there are some methods to come up with better categories.
Thank you also for a very good presentation. My name is Richard Sinding Larsen, and I wanted to ask you if you see any metallogenetic correspondence between the maps of Sweden and the metallogeny of Sweden.
We haven't got through that actually, but my colleagues can answer that question better because part of that project was a kind of collaboration between University of New South Wales and Geological Survey of Sweden. That part is actually, I provided them with the maps, the models, and I have some colleagues over there, they would interpret that in that term. Because this is just, the one in Sweden was just a reconnaissance study. That's why the sampling network wasn't that dense. The distance between the samples were averagely around 12 kilometers. But if you go and do some detailed studies, then we can come up with better understanding about your question.
Someone right at the back behind you.
I have a question. I found that you use Gaussian
simulation?
Yes, Gaussian simulation to the geochemical data, but you use front modeling to identify the anomaly. So they are totally different distribution probability. So I think they are conflict. So how do you think about these questions?
Did I get it? I'm not sure if I got the question, but what you meant was between the simulation method and the classification method we have conflict. I didn't get that point actually. Can you clarify that further?
I mean, the Gaussian simulation will produce the data probably like a normal distribution. But front modeling is favorable for some log normal distribution or some extreme inference or some.
Here we didn't apply any fractal modeling. Here we didn't use any fractal models in this case. You're talking about this model, right? We didn't use any fractal model. This is not a log plot. This is a plot based on uncertainty versus return. No fractal or multifractal classification here. That's why Gerald also make a good point about the categorization. This is just some categorization, but yeah, it's not based on multifractal classification. Yeah, I should have clarified before going through these slides, but yeah, these are not based on fractal, multifractal models.
Hello. Thank you. Look, nice presentation, but just maybe I missed this part. When you say efficient frontier, are you actually comparing with this efficient frontier from finance? You can say that just the points on the line are the maximum ones that you can use and know nothing below or nothing above?
This is
Isn't the Markowitz that you're talking about?
For further details about this name, you can use this name because in petroleum engineering they have some methods like this. They call it efficient frontier. You can find it on 2 different books, Shaded et al. 2018 and Kerr's 2011.
I know what I mean, but what I mean is, it means that just the dots on the efficient frontier.
It's just
in theory, they are the ones that you should select. Is that what you're telling us?
No. No. We select based on this, just based on the categories.
Then why to define an efficient frontier?
This is what it's called actually. I haven't made it.
Okay.
I haven't made this name.
We should I guess,
but yeah,
maybe a little bit more into that. Okay.
So, yeah, something scientific that I can't say, yeah, I agree with that or not. Yeah, but this is, yeah, what's out there.
Yeah, because you're talking about decision making and the uncertainty, and yes, the efficient frontier. You come from finance.
See, it doesn't matter if you use this or not. In this case, you just focus on these samples. I mean, these representative points.
But you could also select other ones as well, depending on the return P50. I mean, your frontier is telling you the limit. Is that what you are?
You can select any of these, do the same process, okay, and generate the map for example, category 4, category 5, category. I've done that actually for all these categories. But the one we are actually after is the one with the highest possible and lowest possible uncertainty. These 3 are the lowest possible uncertainty, but only this one is the one with the highest return as well.
Okay.
If you're after something with lower return, it doesn't make sense actually, but yeah, you can generate the map based on this.
For example, I mean, I don't know if I have time, but if we can use an economic model.
Sorry?
I mean, I can use those in an economic model, and which one will I decide I will follow?
This one, as I mentioned. It's pretty straightforward because you always after the maximum return.
Thank you.
One last question.
Congratulations. I have one question. What about the risk and what is the uncertainty? Risk is equal to uncertainty.
This is what I've tried actually. Whenever you talk to industry, when you say like that analytics, data analytics.
Uncertainty is equal to risk in mineral exploration.
Yeah.
So
this is a kind of equal thing when we call that.
yeah.
Like this morning, Michael Page made a nice point based on Jeff Kerr's advice. Just say data analytics to get some funding, right? So when you talk to industry, it's better to use their favorite terminology. If you say risk, this is more acceptable for them. If you talk about uncertainty, it's better to talk with, scientists. If I say uncertainty, they think about Einstein, maybe something like that. Then they say, no, you're not going to get used to it. You're not going to try that. That's the issue. I've tried that actually. I've tried that with different sectors in industry. And whenever you talk about uncertainty, they say, oh no.
Well, that just brings us to a close. There's one last thing to do, and that's to present you with your award.
Thank you. Thank you so much. Thanks, Peter. Thank you. Thank you.